continuing from the previous lecture, I am going to introduce a term called the structure factor. Let me just summarize a bit from the previous lecture. So, from in fact previous two lectures, what we had was we have an incident beam falling on point scatterers which are at the corners of a unit cell. And the scattered beam goes in a certain direction, and we have been trying to find out what is the intensity at point Q, far away from our finite size crystal. This I had called A point, which is the origin, and B is another arbitrary lattice point. Thus, this was the incident beam direction given by the unit vector S naught. This is a scattered beam direction given by the unit vector S, and the distance of the point Q where we are interested in the intensity is R. So, this vector R we saw was nothing but the lattice vector U A bar V B bar plus W C bar, where U V W are integers. Then we also saw that the amplitude at the point Q can be written as phi 0 upon R e to power I omega t, summing up all over all the lattice translation vectors for our finite size crystal as summing up e to power I 2 pi upon lambda, the dot product between the lattice translation vector and the scattering vector, where the scattering vector S is the difference of the two unit vectors. We also saw that this summation term would have a maxima when the so called Laue conditions are satisfied, which is S dot A equals H lambda, S dot B equals K lambda, S dot C equals L lambda. So, these are my Laue conditions. And H, K and L are integers. And we also saw that this H, K and L can be considered to be a plane H, K, L in crystal space, which is perpendicular to the scattering vector S. So, here, and one more comment I would like to make, phi 0 is called the scattering power of an atom. So, in this equation it basically represents the amplitude after the wave is scattered at a unit distance from the scattering center. This phi 0 would be higher for heavier atoms having larger atomic number as opposed to lighter atoms which have smaller atomic numbers. So, therefore, the intensity, it is important to know that the intensity of the scattered X-rays will be governed by the kind of atoms that are present in the crystal. And here we have, in our previous analysis, we have done analysis of scattering when scattering centers or atoms are at corners of the unit cell. But our real crystals are going to have scattering centers or atoms not only at the corners, but at other locations as well. It depends on how many atoms are present in the unit cell. So, now what we are going to do in this lecture, I am going to extend this analysis. So, let us extend it. So, extension of analysis. So, let us see that, for example, suppose I consider a crystal which has atoms at the corners and I also have an atom, let us say, in the body centered position. So, effectively I am going to have two atoms in this unit cell, and this body centered atom may be different from the corner atom or may be same. Therefore, the scattering power will also be different. For example, at the body centered position, the scattering power may be phi 2, and at the corner atom, the scattering power may be phi 1. So, I have basically in the unit cell two atoms with two different scattering powers. So, for example, cesium chloride could be an example for such a crystal. Now, there can be even larger number of atoms. For example, if I take sodium chloride. Now, chlorine ions I can put at corners and all the face centers, and sodium ion I can put at body centered position. So, body center and edge centers. Effectively, we have 4 chlorine ions and 4 sodium ion per unit cell. So, total of, in this case, there are going to be now 8 atoms in the unit cell, and again I have 2 different kind of atoms. There can be a situation where all the 8 atoms could be different. So, we want to now solve this problem of scattering in a very general way. So, let's look at it like this, that in general I can have m atoms per unit cell, and their scattering power, let me call them as phi 1, phi 2 to phi m. So, in general they can all be different. Then they will have some position vectors, and that, let me call that as rho 1, vector rho 2 to rho m. So, now these vectors rho 1, rho 2, rho m. So, for example, if I consider this cesium chloride where I have 2 different atoms. So, rho 1 could be a vector at 0, 0, 0, rho 2 could be a vector at half, half, half. So, here in crystal space for these vectors rho 1, rho 2, rho m, which will be defined by a particular origin in the unit cell. So, for example, this can be the origin, and they will be defined by fractional coordinates. Now, consider how many atoms are now present. So, the total number of atoms that would be present would be, I have, let us say, n1 unit cells along the A axis, n2 unit cells along the B axis, n3 unit cells along the C axis, and for each unit cell I have m number of atoms. So, the total number of atoms present in my finite crystal now is n1, n2, n3 multiplied by m. If m is equal to 1, then it is just the case that we have already discussed. So, now the summation, this particular summation will change. Now, we have to do a summation of scattered rays over the following vectors: r plus rho 1, r plus rho 2, all the way to r plus rho m, where vector r, which is a lattice translation vector, would be UA plus VB plus WC. So, it is a very simple extension to this, that all I have to do now is summation over these vectors, and the R itself will vary from given by U going from 0 to n1 minus 1, V going from 0 to n2 minus 1, W going from 0. So, let me just write that in this, for vector R, U goes from 0 to n1 minus 1, V goes from 0 to n2 minus 1, and W goes from 0 to n3 minus 1. So, let me now write the modification to this equation, in which I can now incorporate m more atoms per unit cell. Now, this then the wave disturbance at the point Q can be written as e to power I omega t divided by r summation over all the r vectors and now I cannot have the scattering power outside the summation, because the scattering power itself is now going to be dependent on the m different atoms that are present. So, phi 1 e to power I 2 pi upon lambda times r plus rho 1 dotted with the scattering vector S. Second term, phi 2 e to power I 2 pi upon lambda r plus rho 2 dot S, and so on all the way to m terms. Phi m e to power I 2 pi upon lambda r plus rho m dotted with the vector S. So, this is how this equation will change, but you can see now that I can decompose this bracketed term into two different terms. I could take e to power I 2 pi upon lambda times r dot S as a common factor in each of these terms. So, they can be taken out, and the resulting function then would be e to power I omega t divided by r, and now let me take that term out, r dot s term out, and what is remaining would be phi 1 e to power I 2 pi upon lambda rho 1 dot s, second term here phi 2 e to power I 2 pi upon lambda rho 2 dot s all the way till phi m e to power I 2 pi upon lambda rho m dot s, and this whole thing has been taken out of the summation because it is not dependent on the vector r, the lattice translation vector, and what is left inside the summation is the familiar term e to power I 2 pi upon lambda r dot s. Now, this is a term which we are very familiar with, and we know that this goes to a maxima when the Laue conditions are satisfied. S dot A equals h lambda, S dot B equals k lambda, S dot C equals L lambda. So, we will analyze this function only when the Laue conditions are satisfied, because there is no point analyzing this when the Laue conditions are not satisfied. When the Laue conditions are not satisfied, the intensity of the scattered beam would be 0. So, when Laue conditions are satisfied, or we can also say when Bragg condition is satisfied, then we want to analyze this term, because then the intensity will be governed by what would be the magnitude of this term, which has now individual atoms inside a unit cell. Let me call this term as capital A, which is also called as structure amplitude. Why this name structure amplitude? Because this has information regarding the structure of the crystal, that is the atoms, what atoms are present and their locations inside the unit cell. So, this term is then now limited only to the atoms that are located in the unit cell. Now, let me write this structure amplitude in an abbreviated form, because I can put a summation now, that I have m number of atoms in the unit cell. So, j is equal to 1 to m, the scattering power of the individual atom, let us say phi j, multiplied by e to power I 2 pi upon lambda rho j dot s. So, now very clearly, if A goes to 0, the scattered beam intensity will also go to 0, even though the Bragg condition is satisfied or the Laue conditions are satisfied. Now, let us further simplify this. Let us write rho j in crystal space, because rho j gives me the location of the atoms inside the unit cell. So, rho j in crystal space is very simple. This is written as uj A plus Vj B plus Wj C, where A, B, C are the unit cell vectors, and Uj, Vj, Wj are fractional coordinates of the location of the jth atom. So, fractional coordinates for the jth atom, and phi j is the scattering power of the jth atom. Now, substitute the rho j vectors into the structure amplitude equation. So, I can then write A equals j going from 1 to m phi j e to power I 2 pi upon lambda, and then I can put the vector r j in it. So, it can be written as u j s dot A plus v j s dot B plus w j s dot C. But now we are analyzing the structure amplitude when the Laue conditions are satisfied. So, S dot A is h lambda, S dot B is k lambda, S dot C is L lambda, which means basically this is h lambda, this is k lambda, and S dot C is L lambda. If we substitute this, I will get the structure amplitude as j equals 1 to m, and you can see this wavelength lambda would get cancelled out, and what I am left with is phi j e to power I 2 pi h u j plus k v j plus L w j. Now, this is an important equation that we have arrived at. So, h, k and L are representing the planes from which X-ray reflection is taking place, and u j, v j, w j are the fractional coordinates of the atoms in the unit cell. Now, in order to slightly modify this equation a bit further, let me define two terms. So, let me define something called as the atomic scattering factor, we will denote it as small f, and this is defined as f equals amplitude of the wave scattered by an atom divided by amplitude of the wave scattered by a classical electron. Essentially, what we are then trying to say that the scattered amplitude, which is also given by the scattering power phi. So, phi being the scattered amplitude will be f multiplied by the amplitude scattered by a single classical electron. This also indicates this atomic scattering factor f is going to be a function of the number of electrons in the atom or the atomic number. Similarly, let me define one more factor. At this time, this factor is called as the structure factor. The structure factor use the symbol capital F, and this is defined as amplitude of the wave scattered by all atoms in the unit cell divided by amplitude of the wave scattered by a single classical electron. So, now if I look at the structure factor equation, or rather the structure amplitude equation, the structure amplitude equation was A equals summation j equals 1 to m phi j e to power I 2 pi h u j plus k v j plus L w j. Now, instead of this, I could just divide both sides by the amplitude of the wave scattered by a single electron to obtain the structure factor equation, which you may have read about a bit. And this structure factor equation simply then becomes F equals summation j equals 1 to m, and instead of phi j I replace it by the atomic scattering factor F j multiplied by e to power I 2 pi h u j plus k v j plus L w j. This is a very important equation in X-ray crystallography. And one more thing to note, that small f the atomic scattering factor and the capital F the structure factor, they are simply pure numbers. With no dimensions. Now that we have defined the structure factor, and another thing that one can note is that the intensity of the diffracted beam would clearly be proportional to F star, the product of the structure factor multiplied by its complex conjugate. So, let us say that Bragg's law or Laue conditions are satisfied. In that case, I intensity will be 0 when F the structure factor goes to 0, and this is what we call as extinction of the scattered beam. And this structure factor will come out to be very useful in analysis of crystal structure. So, I conclude this lecture here. In the next lecture, we will do some calculations based on the structure factor. Thank you.